In this video, we're going to look at what are called oxidation numbers or oxidation states, which will be a way for us to account for electrons. It works for both ionic and molecular compounds, and we're going to see that ionic compounds, it reflects the charge, but molecular compounds don't have charge. But molecular compounds certainly undergo redox reactions. In fact, many of the reactions that keep us alive as living organisms are redox reactions. In fact, the very cellular respiration and photosynthesis reactions that are very crucial to life are both redox processes. So taking carbon dioxide and water, forming glucose and oxygen, that's photosynthesis, that is an electron transfer reaction. And the opposite, cellular respiration, us taking glucose and oxygen and breaking that into carbon dioxide and water, is also a redox process. So those are all molecular compounds, and we still see those redox things happening. So it's helpful for us then to find a method for determining oxidation and reduction in a reaction when we don't have ions. And so we're going to have 4 rules. These rules apply in order, meaning the first rule always takes priority, and then the second rule, and then the third and fourth rules. So always do them in order. As soon as you have a rule that satisfies your problem, that's the rule you stick with. So let's go ahead and take a look at these rules. So the first rule is any element by itself has an oxidation number of 0. So that could be, for example, hydrogen, or aluminum, or bromine, or sulfur, which often forms these 8-membered rings, or xenon. Anything by itself, meaning it's only got its own element and there's no other element in that component, its oxidation number is 0. Fairly straightforward. Number 2, for simple ions, meaning they are monoatomic, the oxidation number is equal to the charge. So if we look at some simple ionic compounds, aluminum nitride, sodium chloride, and calcium fluoride, the oxidation number is equal to the charge. We already know the charges of these things, and we will write them below. Sometimes you write them above. I typically write them below. Does not matter to me, though. If you want to write them on top, that is just fine. Calcium forms a +2 charge, fluorine forms a -1 charge. Notice that even though there are 2 fluorines, each fluorine is -1. So we always indicate the oxidation number for each specific instance of that element. So for 1 fluorine, it's -1. We don't care that this compound has 2 fluorines. All right, that's for charge balancing. Each fluorine is -1. We report the oxidation number, therefore, as -1. So far, so good. Nothing new here. For compounds, the sum of oxidation numbers must equal 0. And we'll do an example of this actually after we do the 4th rule. But I want to put part B for this. So rule like 3B, for polyatomic ions, the sum of oxidation numbers is equal to the charge. And what I mean by that, polyatomic ions, that's only if you're looking at a polyatomic ion. If your polyatomic ion is part of a compound, follow the compound rule. All right, so if you're looking at a polyatomic ion by itself, that's when you apply 3B. But remember that these rules are kind of in order. So if 3A works, if you have a compound, follow 3A, don't follow 3B. Always apply them in order. We'll take a look at that after I introduce rule B for most things. But for let's just do a simple one. For example, We've done this before, for example. If we have CoCl2, how did we determine the charge of the cobalt in this compound? Because cobalt has variable charge. What we did was we set the charges equal to 0. They have to balance each other out. We can say that this is a compound, CoCl2. In order to find out the oxidation numbers, the sum of all those oxidation numbers must be equal to 0. We know that chlorine preferentially forms -1 ions. They're simple ions, so we can say that. So cobalt plus 2 times -1 is 0. We solve this, cobalt must be plus 2. And indeed, that's how we would do it, right? Or we could do the crisscross and all that fun stuff. But that's how we figured out the charge. And remember, for ionic compounds, because they're made of ions, charge and oxidation number are the same thing for ionic compounds. So that's what we're going to look at. We're going to be doing this kind of simple algebra. Rule 4, though, is going to help us out a lot when we're looking at molecular compounds. In this order, and always this order, give fluorine the oxidation number of -1. These are, remember, in order. So element by itself, 0. A simple ion equal to its charge. For 3A, the compound sum must equal 0. If all else fails, now we look at rule 4. And we do this in this order. Fluorine is -1. Hydrogen is +1. Oxygen is -2. Keep going. Now we come down here. Chlorine will be -1. Nitrogen will be -3. And that's kind of as far as we need to go. We're probably not going to see anything that goes beyond this. So ... If you remember the property of electronegativity, we follow that order. So we go from most electronegative to least electronegative, but that's not something we've talked about yet in this course. So generally speaking, nitrogen should be enough to get everything out of the way. But we have to do these in order without violating any other rules, because this is rule 4. It's the least important one. Let's take a look at some examples here. Let's take a look at calcium nitrate. Let's determine the oxidation numbers of everything in calcium nitrate. Let's look at our rules. First rule is any element by itself. Calcium nitrate is not an element. Doesn't apply. Do we have any simple ions in this, meaning monoatomic things? Yes, we do. Calcium is +2. It is a simple ion. Remember, metals in compounds form simple ions. So great, calcium's done. Next rule is for compounds, the sum of the oxidation numbers must equal 0. Great. So, remember the 3A, this is a compound. This is not a polyatomic ion. This is a compound that has polyatomic ions. So rule 3A applies here. So we have calcium plus 2 nitrogens plus 6 oxygens equals to 0. Don't forget to distribute your 2. We have 2 nitrates here. Go ahead and make that 0. Because we have oxygen and 0, I'm going to put the 0 with a line through it. Right, so we have calcium already solved for, but we don't have nitrogen and oxygen. In order to solve this equation, we can only have one variable left. So that's where rule 4 comes in. We say, do we have fluorine? Nope. Do we have hydrogen? Nope. Do we have oxygen? Yes. Oxygen will prefer to be -2. So we'll give it that. At this point, we now have calcium and oxygen solved, meaning we can solve for nitrogen. Great. So if we plug in our numbers, +2 plus 2 nitrogens plus 6 times -2 is 0. That means 2 nitrogen minus 10 is 0. 2 nitrogen is 10. Nitrogen is +5. And that will be the oxidation number of nitrogen. So, couple things with this. This is not a charge. Nitrogen in this is not acting as a simple ion. So this is not the charge. We are not saying we have nitrogen 5+ in this compound. Oxidation numbers for simple ions are the charge. For complex ions, they are not the charge. The sum is the charge, but they themselves are not the charge. So we would represent nitrogen, therefore, as +5. Now you're asking yourself, well, what the hell? We have nitrogen equals -3 right there. It literally is right there. If we tried to do that, we would violate rule 3. And here's how it works. So if we have 2 plus 2 times -3 plus 6 times -2 equals 0, we get, let's see, -6, -12, so -16 equals 0. We have violated the universe. No good. Can't give nitrogen -3 here. That's why we have to follow these in order. Fluorine gets preference, then hydrogen, then oxygen, then chlorine. So sometimes you will see oxygen that doesn't have -2. In hydrogen peroxide, for example, you can do it. We'll get 2H plus 2O equals 0. Hydrogen is first in our rule order. So we have +1. So 2 times 1 plus 2 oxygens equals 0. 2 oxygens is -2. Oxygen is -1. So in this compound, oxygen is -1. So follow the rules in order. Do not violate rule 3 by trying to apply rule 4. Always do rule 4 in order. Fluorine first, then hydrogen, then oxygen, and so forth. All right? Let's just take a quick look at our original reaction. We had the zinc and the HCl turning into H2 and zinc chloride. Let's take a look at the oxidation numbers of everything in this reaction. Let's look at zinc. 0. How do we know? Rule 1, zinc is by itself. Hydrogen is also by itself. 0. Done. Hooray, we've got half of our reaction done. With HCl, we can consider it a strong electrolyte made of ions. So, +1, -1. Great. Zinc chloride is also an ionic compound, meaning we just have the charges. Ta-da! When we look at these now, we can take a look at the reaction and say, aha, we have zinc, hydrogen, and chlorine in this reaction. Zinc starts at 0, hydrogen starts as +1, chlorine starts as -1. Zinc becomes +2, hydrogen becomes 0, chlorine becomes -1. We therefore can say this is the oxidation, and this is the reduction. Reduction means you are decreasing your oxidation number. Oxidation means you're increasing your oxidation number. Reduction is probably easier to remember because the number gets smaller. And it reduces. That's, in English. Reduce gets smaller. So we can say that. So that is the concept of oxidation numbers. You can apply it yourself. Take some examples. You can have oxidation numbers of 0, by the way, in other compounds. The best thing for this, though, do this one on your own and see what you get for the oxidation numbers and see what's oxidized, what's reduced. This is a redox reaction, by the way. Do this one on your own, see what you get, and you should see this as a redox reaction. With this, very often, by the way, we don't need to balance these if we're just doing redox. That's a word of warning and a good thing. No need to balance if doing just oxidation numbers. For example, we didn't balance the hydrogen and the chlorine here. That doesn't matter. We don't care that zinc went to 2 and hydrogen went from 1 to 0. Who cares? All we need to see is a change. Zinc has become more positive. That's all we care about. Doesn't matter how positive, right? hydrogen became smaller. Nothing changes. If we throw a coefficient in there, nothing changes in this reaction. So the oxidation number of hydrogen still is +1. It's still becoming 0. So we don't need to balance it. If you balance it, might be a waste of time. So just be aware of that. You do not need to balance if you're only doing redox stuff. So you can do this combustion reaction without having to worry about balancing it. You can do the oxidation numbers. All right, and I'll put the oxidation numbers in the notes so you have them, but we will not have it on the video. All right, so in our next video, we're going to take a look at solutions and solution stoichiometry.